EDX Decision 1, Graphs and Networks 2, Shortest Paths and Route Inspection. The route inspection problem. So quick recap. Is this graph Eulerian? In other words, is it traversable and how can we tell? If you want to take a second to just pause the video and try and check in this, you're welcome to. So a test for traversability is, can we draw this diagram and draw every edge once and get back to our starting point? And that's the premise behind the algorithm we're going to be using in this session. A good analogy is to imagine there's been a fall of snow on a network of country lanes and the snowplow wants to clear every country lane, ideally travelling along each road only once, if possible. So imagine that the edges in the network are streets and the weightings are the lengths of the streets. The idea is that you want to walk along every street at least once, and ideally once if possible, but you want to cover the shortest possible distance. You usually want to start and end at the same node. We think of this as route inspection, as this is what you would do if you wanted to inspect the whole of the network. A postal worker would also have to do this when delivering mail. The solution to this problem was studied by Chinese mathematician Quan Mai Ko in 1962. Hence, we often call this the Chinese postman problem. So if a graph is Eulerian, in other words, if all the nodes have even order, then the solution is straightforward. You would simply need to use each edge once and the minimum weight would be the sum of all of the weighted edges. However, if it is not Eulerian, then we have to use some of the edges more than once. We only want to reuse edges that join odd nodes, but we need a way to do this systematically, and that is achieved with the route inspection algorithm. So I'll just talk you through the algorithm and then we'll put it into practice. So the first thing we do is identify and list all the odd nodes in the network. We'll consider all the ways of pairing up these odd nodes and write these down with their weightings. We select the combination of pairings with the least weight. We find the sum of all the weights of all the edges of the network. We add together the results from steps 3 and step 4, and this will be the least possible value for the route inspection problem. And if required, we can then find a tour of the node which repeats the edges in step 3. So here's an example. We want to travel along every edge at least once in the most efficient way possible. So first we've got to do is to identify the order of the nodes. So A has got 2 connectors, that's order 2. B, 3 connectors, that's of order 3, and I'll circle that just to make it stand out. D has 4 connectors, that's fine. C has 4 connections. E has 3 connections, so again there's the odd node, and F has 2 connections. So we've got to now find a way of connecting B to E in the most efficient way possible in order to make them even nodes. I'm not going to go B, D, D, E because that's an extra 4, and I'm not going to go B, C, C, E because that's an extra 4. I think I can achieve it in the most efficient way by going B to C, then repeating C to D, and then repeating D to E. So if you now look at the order of the nodes, B is order 4, so that's okay. D is order 1, 2, 3, 4, 5, 6, so that's still okay. C is order 1, 2, 3, 4, 5, 6, so that's still okay. And E is order 1, 2, 3, 4, so that's not a problem. So we can now traverse this new network, and I'll show you an example. If we start at A, we could travel to B, down to C, repeat CB to get back to B, along to D, down to C, repeat CD to get back to D, down to E, repeat ED to get back to D, over to F, and then along the bottom across to E, to C, and back to our starting point A. And the total weighting would be the original weighting for the problem, so the original network added up to 25, and then we've repeated BC, CD, DE, so that's an extra 3, so it adds up to 28. Is the shortest, most efficient way of travelling along every edge at least once. What about if we have two pairs of odd nodes? So in this slightly more complicated network, I'm going to go through looking for the odd nodes. 3 is odd, B is odd, C is odd, and I is odd. All the other nodes are even. You will always have an even number of odd nodes. So we've got 4 odd nodes. So to make this problem traversable, we need to make the odd nodes into even nodes. So we need to look at all the ways of pairing them up. So we could connect A to C and then connect B to I. So the most efficient way of connecting A to C is to repeat the top edge. So that's an extra 150. And the most efficient way of connecting B to I is straight down the middle, B to E, an extra E to G, and G to I would be an extra 450. So the total extra there would be 600. Another way of pairing them up would be connect A to B and C to I. So connecting A to B is an obvious extra 100. And linking C to I, the best way of linking C to I is 200, the extra 160, and the 80. So that adds up to 440. So that's an extra 440. So that adds up to 540 extra. And the final way of pairing them up is to connect A to I and B to C. The most efficient way of connecting A to I is repeat AD, repeat DG, repeat DI. So that would be an extra 380. And B to C is the direct link of 120. So that adds up to 500. We can now see, looking at these 3 possible solutions, the most economical one is the extra 500. So our total weighting now is the weighting of the original network, which is given as 2090. Then we need to connect in A to I. So to connect A to I, I'm going to repeat AD, I'm going to repeat DG, and I'm going to repeat GI. Now, and I'm going to connect B to C directly. Now if you check the order of the nodes, A is order 4, so that's good. B is order 4, that's okay. C is now order 4, so that's fine. D is order 1, 2, 3, 4, 5, 6, so that's still okay. G is order 1, 2, 3, 4, 5, 6, so that one's still okay. And I is order 4, so that one's okay. So we now get the total weighting as the original 2090 plus we need an extra AD and an extra DG and an extra GI and an extra B to C. So this problem will be traversable with a solution, adding it all up, of 2,590. What if there are more than 2 odd pairs of nodes? So So the algorithm can still work if there are more than 2 odd pairs of nodes, but it will be much more complicated. In practice, if there were, for example, 6 odd nodes and we had 3 pairs of odd nodes, it would be impractical in an exam question to look at all the different ways of pairing up all of those odd nodes. But you would need to explain that, the principle behind it, if required. Some of the common errors with route inspection problem. Giving an incorrect order for a node at the starting point. Not checking carefully for all the possible pairs of odd nodes. This is particularly if there is a shorter indirect route between 2 nodes than the direct route. It is possible to miss that improved solution, so always check very carefully. Giving an incorrect total for the final answer. So that brings us to the end of shortest paths and route inspection.